my channel. I'm Rachna, pursuing my third semester of BE Computer Science from Sri Venkateshwara College of Engineering. In today's video, we are going to learn about stochastic processes, probability vectors, stochastic matrices, and its applications. So these are the subtopics which we will cover under today's topic. So without any further delay, let's get started. Introduction to stochastic processes. Definition. A stochastic process is a collection of random variables indexed by time or space. It models systems where outcomes are uncertain but follow probabilistic rules. Examples are stock price movements, population growth, random walks. Key components are state space, time index. State space refers to the set of all possible states. Example, sunny, cloudy, rainy, and all. And time index represents evolution. So it can be discrete or continuous. Why should we study stochastic processes? It is to understand and predict dynamic systems under uncertainty. Probability vector. What is a probability vector? A vector P, which is equals to P1, P2, and P3, and so on up to Pn, let's say. And here the condition applies that Pi is always greater than or equal to 0 for all values of I. And sum of Pi values is always equals to 1. These two are the conditions for probability vectors. Interpretation. Each entry Pi represents the probability of being in state I. Here is a small example. For a system with 3 states, P is equals to 0.3, 0.4, 0.3. Here it shows that there is a 30% chance of state 1, 40% chance of state 2, and 30% chance of state 3. The significance is probability vectors provide a snapshot of the likelihood of various states. Stochastic matrices. A stochastic matrix represents transitions between states in a stochastic process. Rows are probability vectors. Properties are it is non-negative entries and rows sum is equals to 1. Here is another example. Transition matrix for weather states. Sunny, cloudy, rainy. Here is a transition matrix which is represented by P. The interpretation for this matrix is, let's assume today is Sunday, then there is an 80% chance that tomorrow is sunny again, and 10% chance it's cloudy, and 10% chance it's rainy. Transition dynamics. How it works. Use matrix multiplication to compute the next state distribution. Here is the formula. P to the power of t plus 1 is equals to P of t dot P. Example, for initial state P of 0 is equals to 1, 0, 0, 100% sunny. After one step, P of 1 is equals to 1, 0, 0 dot. Here this is the matrix which we have seen in the previous slide. Here, this same matrix, the P value, we have put that in this one. So when we do the matrix multiplication, P of 1, we get it as 0.8, 0.1 and 0.1. So now the applications are finance, AI and machine learning, epidemiology, physics, operations research. Finance. Stock market modeling using Markov chains. Portfolio optimization under uncertainty. AI and machine learning. Markov decision processes, MDPs, for reinforcement learning. Natural language processing for predictive text. Epidemiology, predicting disease spread. Example, SIR models. Physics, particle behavior in Brownian motion, operations research, modeling queues in service systems, traffic flow analysis. Case study, weather prediction example. So here we'll take a small case study example of weather prediction example. States are sunny S, cloudy C, rainy R. Initial probability vector will be P of 0 is equals to 1, 0, 0. And the transition matrix is the same one as before we have seen. And here is the question. What is the weather after 2 days? So to predict that, here is the calculations. Day 1 will be P of 1 is equals to P of 0 dot P. And day 2 will be P of 2 is equals to P of 1 dot P. And advantages and limitations. Advantages, models uncertainty systematically, widely applicable across disciplines, enables predictions and decision making. Limitations are requires accurate data, computational complexity for large systems, sensitive to initial conditions and assumptions. So finally coming to the conclusion of today's video, key takeaways. Stochastic processes model dynamic systems under uncertainty. Probability vectors and stochastic matrices are foundational tools. Applications span finance, epidemiology, AI, and more. Final thought of today's video is understanding stochastic systems is crucial for tackling real world problems involving randomness.